This is a brief explanation of the pages I look at in Rasp. So here we are at rasp.nz. I'm going to choose a region and a forecast confidence of high for Saturday, and here we are at the forecasts page. So on the right are the viewing options, and I'm going to use the viewer, and I'm going to look at thermal updraft, velocity and buoyancy shear ratio first. There's two things I'm looking for here: thermal strength and how easy the thermals are going to be to work. So with the thermal updraft velocity, that's depicted by the colours on the map, and you can see, for example, here we have orange and yellow. If we look down at the key on the bottom here, orange and yellow, that's sort of 500 to 700 feet per minute, which is good lift. I would probably go flying in anything over sort of 300. And the second thing we're looking for is the buoyancy shear ratio. It says how easily the thermals are going to be to work, and that is depicted by the stipple or the black dots, or the lack of black dots on the map. So with no stipple in this area circled here, we have no dots, so that's very good. That's what we want. We have sparse stipple here. You can see the dots are sort of spaced apart a little bit. I would still go flying if I saw that, as long as everything else in the forecast was good. And then we have dense stipple down the bottom here. The dots are really close together, and I probably wouldn't go flying if I saw dense stipple. The next thing I would look at would be wind and lower level forecasts. So we're going to look at surface wind, boundary layer, average wind, and convergences. So surface wind is going to look at the speed and the direction of the wind at 10 meters above the ground. So the speed of the wind is depicted by the colours on the map, and refer to the key down the bottom for knots. And direction is indicated by the lines and arrows. So you can see looks like a convergence day here with wind coming in from either side of the island. So that is surface wind. Boundary layer wind. This is the average wind speed and direction through the boundary layer. So again, it's the same thing. It's colours on the map, key down the bottom for knots, and same thing, arrows and lines for wind direction. Convergence. Convergence is indicated by, you can see these lines on the map with the yellow and orange lines of convergence. And again, we've got a key down the bottom, a lot of yellow and orange and red. So quite good convergence, 150 to 200 feet per minute up. And you can see patches of light blue, which would be sort of 50 feet per minute sink. So that's how to read the convergence page. Now we're going to look at the Skew-T for Moyers Hill Hang Gliding and Paragliding Club. Okay, so this is the Skew-T graph. On the right hand side we have altitude from 0 to 32,000 feet, and across the bottom we have temperature from minus 30 degrees up to positive 40 degrees. The only lines on this graph that change, the main part of the graph, are the red actual temperature line, the blue dew point temperature line, and the dotted black line, which is the lifting air line. All the other lines behind are just reference lines, and I'll just go through and highlight each of those and explain what they are. So these are isobars, or height, the horizontal lines. For example, if I want 8,000 feet, I just draw a horizontal line across. 14,000 feet across. Isotherms, this is basically the temperature. So if I look at 0 degrees, the line going up on an angle here to the 0 at the top is 0 degrees. The next one over is 10, 20, 30, etc. So the temperature is read on that angle. These lines are the dry adiabats, or the dry adiabatic lapse rate, and they just indicate the cooling of the air, 3 degrees per 1,000 feet. And this is the saturated adiabatic lapse rate, so these lines reference the cooling of the air at 1.5 degrees per 1,000 feet. So I've labelled a few other things on the graph here for you. What I'd like you to take note of is the inversion, which is where the red line turns sharply to the right. This area here, as it increases with temperature and altitude before it starts going back to the left again. And the next thing to look at is the black dotted line, and you see that, I want you to think thermals, convection, lifting air, sometimes called a lift line. And you can see the line starts out running parallel to the dry adiabatic lapse rate, and then it changes direction and it follows the saturated adiabatic lapse rate line. Now where it changes direction is where it turns into cloud, so that's where cloud base is going to be, just over 2,000 feet. And this line here where it hits the inversion, about 5,500 feet, will be cloud tops. So that's the first thing I want to look at, cloud base, cloud top. That's reflected on the left as well with the low cloud. And I want to look at the wind, which is in this area here. And off this line here we've got lots of lines and barbs, and that gives us the wind strength and direction. So for example, right up the top here we've got a westerly 30 knots, and right down here about 8,000 feet we've got an easterly 10 knots, and there's some examples there to show you how to read it. We've also got this line here which shows the wind speed, so we've got 0, 20, 40, 60 knots, so we're starting at about 30 knots up here, down to 20, down to 5, and coming down back up to 20 again just about. So that'll show you the wind speed at altitude. So now we're going to look at a good day. So first thing I want to look at again is cloud base, and if you look at the black dotted line you'll notice that it follows the dry adiabatic lapse rate, but it doesn't change direction, and that's because it doesn't condense into cloud, so it's going to be a blue day. So cloud base is at 4,500 feet. You can see there's a bit of distance between the blue line and the red line, which also indicates that it's going to be a blue day. You can see on the left, we've got some high cloud up there. And this flight was actually a 78 kilometre out and return flight that a pilot did, and he reported mostly blue. Convergence had light winds and just enough cloud to mark it, so the high cloud mustn't have affected him very much. And we can see the wind here is about 5 knots up to the inversion, and it's southwest, so quite light. On the right hand side here we've got the thermal updraft velocity page, and that is yellow, so it's about 500 to 600 feet per minute with no little black dots or stipple on it, so that looks very good. If we go to the convergence page, the area that the pilot's flying in is this area here, and we can see that the convergence goes through that area, and on the right we can see the pilot's track log took a similar path out and back. Here is a bad day, so we've got on the left we've got high cloud and low cloud. We've got a 2,000 foot cloud base just over. We've got 18 knots of wind, and you can see where the blue line and the red line touch. There's possibly going to be rain as well. Overdevelopment. This is what overdevelopment and thunderstorm potential looks like. If you look on the Skew-T, you can see that with our lift line changes direction there, so cloud base is about 2,500 to 3,000 feet, but there's only a very small inversion there, which is not enough to stop the saturated air from just going all the way up to about 28,000 feet. So this day was forecast for thunderstorms, and I'm not surprised. On the right you can see the Cape page has a lot of dark reds in it, so that's a very high value as well. And the Cape value is also here on the Skew-T. So the really high values like that, overdevelopment, thunderstorm potential. And I'm going to leave you with the Cape page, the convective available potential energy as well. So yeah, cheers, hope that helps.